We have observed the North Star for a very long time. The actual North Star changes due to precession. Our current North Star is Polaris and sits almost directly above Earth's North Pole, and can be used to navigate north without using a compass. As our telescopes improve, we observe more and more of the heavens, and we start to learn more about the nature of the universe. But in some cases, these added observations reveal fundamental misunderstandings about our assumptions of stars themselves. Let's explore why Polaris has got scientists so stumped. Polaris is about 300 to 400 light years away from us. It is known as a Cepheid variable star. These stars change their brightness and diameter on a very regular basis. Polaris is actually the closest of these types of stars to Earth. It is also not alone. It is a binary system. Its sister star is known as Polaris B, and can actually be observed orbiting this star from Earth. Now, as you can tell, one of the problems with this star is accurately measuring its distance. There are a number of different ways that this can be done. One is based on the stellar evolution of a star. By studying the brightness, color, and rate of pulsation of the star, they then figure out at what stage of its life cycle it is, and therefore how bright it should be. From here, it is relatively simple to work out how far this star is away from us. And this is one of the main ways we can tell distance beyond the simple parallax. Scientists believe that they understood this relationship between the evolution of the star and its periodicity and color to accurately measure the distance. But Polaris has thrown a large spanner in the works. Now, there are a number of different ways to calculate the distance to a star. An alternative method is using the fact that this star has a companion which can be seen orbiting it. Using simple equations, the mass of the star can be calculated. Combining this information with Hubble's new parallax measurement system, and you have a different way to calculate the distance. Using these measurements yields a mass of about 3.45 times that of the Sun. The problem is, using the star evolution method, you should end up with a value which would be 7 times bigger. Even stranger is the fact that when they examine the age of Polaris B using the evolutionary model, it comes out that this sister star is much older than the larger sibling. Typically, binary stars are the same age. One possibility the researchers suggest is that the larger star may once have been two smaller stars that collided with each other, rejuvenating the star, but they point out that this is an unlikely scenario, but not impossible. They go on to state, it is challenging to draw significant conclusions beyond the fact that Polaris continues to be an enduring mystery, and the more we measure, the less we seem to understand. This once again illustrates the problem we have in trying to understand distances to local stars, let alone distances to other galaxies. A lot of distances are calculated using Cepheid variable stars, from the distance to galaxies in our local group and beyond to the Hubble constant. If the underlying assumption of what these stars are is incorrect, then a vast majority of the distances are therefore also wrong. We just happen to be lucky enough in Polaris's case that we are close enough to be able to use different methods to calculate the distance. The mass discrepancy in Cepheid variable stars is nothing new. In fact, it was first reported in the 1960s, and since then many more cases have been found. The differences in most of these cases was only about 20 to 30%, so Polaris blows this totally out of the water. So what exactly are Cepheid variables? These are a special class of stars. They are yellow, bright giant stars, and their radius changes by as much as 25% during each pulsation cycle. The pulsation cycle is typically between 1 and 50 days. So why do they pulse? The accepted explanation is called the Eddington valve. Helium is the gas that is thought to be the most active in this process. Double ionized helium is more opaque than singly ionized. The more the helium is heated, the more ionized it becomes. At the dimmest part of the Cepheid cycle, the ionized gas in the outer layers of the star are opaque, and so is heated by the star's radiation, and due to the increased temperature begins to expand. As it does so, it cools and becomes less ionized and more transparent, allowing radiation to escape. The expansion stops and reverses due to the star's gravity, and so the process repeats. So how could we explain these in an electric universe? There are a number of alternatives. The first is simply that the incoming current varies or pulses, which causes the star to change brightness over these pulsation periods. The problem here is explaining why the incoming current would vary at such a regular interval. You would also expect that stars upstream and downstream would be affected by this pulsation. So, in effect, we would be able to see Cepheid star streams, which as far as I know, we do not see. If we closely examine the luminosity change of these types of stars, they seem to match that created by lightning, but on a longer time frame. A key also lies in the fact that these are binary systems. Don Scott elegantly explained it as follows. Each of the stars has an electric capacitance. These two capacitances are permanently connected by a plasma cloud. This plasma exhibits a non-linear resistance. If one of the stars charges up to a high enough voltage, then the plasma will go into arc mode and emit brilliant light. Electrical energy will be transferred from the first capacitor star to the other. The bridge between the two stars probably doesn't go away. After the arc discharge is over, the plasma in the bridge will go from arc mode back into dark mode until the next discharge. This would explain not only the variation in the brightness, but the change in size due to the discharge in the plasma cloud. If we examine Polaris, another interesting fact is that over the last century, the brightness has increased while the level of variability decreased while the length of the periods has increased. And this shows that this bridge will not last forever and stars will naturally evolve to a more equilibrium state. Now, one other important point to remember is that in the Eddington valve model, we have plasma that is opaque and plasma that is transparent. Higher ionization creates more opaque, but is dimmer. But if we consider plasma redshift, the idea says that greater ionization and hence free electrons equals greater redshift. Now, this creates a problem. If we examine Cepheid variables, we know that the majority of them actually end up with quite a high redshift. So mainstream sees these higher redshift Cepheids as more distant, and as proof they cite that the redshift Cepheids are also dimmer. So could it be that some of these Cepheid variables have higher redshifts because they have higher ionization compared to others? So our reliance on Cepheid variables as distance measurements really should be called into question. One interesting question is trying to understand how a Cepheid system is set up in comparison to other electric stars we look at. Is this an unusual configuration, or is this something that happens when a binary twin is ejected for a short period of time until the system stabilizes? As always, be brave, be curious, the truth is waiting for us. Until next time.